To mathematics class. We had a session last week. I'm sure you have gotten to those sessions. If you have not watched our class last week, make sure to do so. The link would have definitely been provided to you. Catch up. In today's session, we will continue along mathematics just as we saw in the previous session. Last week, we started on the topic calculus. We said we were going to take mathematics as branches. We talked about the algebra, we talked about calculus, we talked about probability, we talked about statistics, and all of those different branches. And we started off with the calculus branch. Last week, we were able to create a very good flow in terms of the introduction to calculus, as well as the introduction to one of the most important topics in calculus, which is talking about differentiation. On that differentiation, we discussed on the concept of limits and continuity, where we linked that limit simply talks about the, the closeness in value from a particular variable to a particular point. Closeness in value. So if I say limit as x tends to 3 of x squared is equal to 9, then I'm saying that whenever x becomes very, very similar to 3, then x squared becomes very, very similar to 9. That's the concept of limit, which we looked at in detail in the last class. We also extended this concept of limit and said it plays a very, very vital role in how we deal with differentiation. We talked about the different standard differentiations we had, the differentiation of algebraic terms, the differentiation of trigonometric terms, the differentiation of exponential terms, as well as the differentiation of logarithmic terms. We looked at all of that. And then we now said that these standard terms that we have, they are possible because we can simply discover those standards by using limits and continuity. To round off, we discussed on the concept of the L'Hopital rule, or what is colloquially called L'Hospital rule. But for the L'Hopital rule, we talked about the fact that we could evaluate limits of fractions such that the denominator is either 0 or the numerator and denominator are infinity. In that case, it becomes undefined. If that is the case, then L'Hopital rule tells you that you can take the numerator and the denominator separately and then differentiate them, and then the new result you have, you take the limit on that result. Taking the limit there immediately allows you get the result that is going to be defined. If, however, you take the limit and it's still undefined, then you repeat the process, which means those new sets, those new numerator and denominator you have, you differentiate it again. That way, you continue the process until you get a value that exists. So that is what the L'Hopital rule talks about. A good example is if we take limit as x tends to 2 of x plus 3 divided by x minus 2. In this case, if we evaluated the limit directly, we will be having 5 over 0, which is undefined. So instead of that, we differentiate. So if we differentiate by L'Hopital rule, L'Hopital says we differentiate numerator separately, so it becomes limit as x tends to 2. Differentiate numerator separately, you have 1, because the differentiation of x is 1 by standard differentiation, and the differentiation of 3, which is a constant, is 0, divided by the differentiation of 1, the x here is 1, and the differentiation of 2 is 0. So in this case, you see that the limit as x tends to 0, x tends to 2 of 1 divided by 1 is still going to give you 1. Why? Because there is no x in which you want to evaluate here. So you have 1 divided by 1 is 1. So you've gotten yourself a defined value, unlike the first step where you had undefined. So that is why L'Hopital rule is very, very important. I'm sure all of this and more, you have seen it already in the session we had last time out. If you have not watched it, make sure to go through those sessions. That's why we have the recordings available. Today, we will continue on that concept and start taking differentiation as a whole. So if you have not gotten it, take this moment, get your pen, get your paper, make sure you are ready for class. So let's start. We will first and foremost begin with first principles. First principle. This is very, very interesting. In mathematics, we realize that just like you have it in, let's say, quadratic equations, and you could solve quadratic equations using quadratic formula, but instead you could decide to take the completing the square method, which is like the extended form before you get to the quadratic formula. Same thing happens to differentiation. While we could easily differentiate some terms by using their standard forms, we can also go through the pains of following the process step by step in order to carry out those differentiations. Let's take simple examples. For instance, whenever we have y to be equal to x squared, then dy dx simply says by the rule, take 2, multiply the coefficient of the variable, that's 2 times 1, and then you return the variable and then subtract 1 from the power. So your final result becomes 2x raised to power 1, or you write as 2x. This is a standard notation. But then, how did we move from here to here? We can show this by using first principle. And that is what we want to showcase today. Now, where do we start from? Remember, when we said dy dx, we explained that this means that an increase in y causes an increase, or an increase in y is caused by an increase in x, right? So we say differentiate y with respect to x, which means the change happens in x and it causes an increase in y. X is the independent variable, whereby y is the dependent variable. So this is the independent variable, this is the dependent variable. So that is the full nature of differentiation. That change with respect to the dependent variable, with respect to the independent variable, caused by that independent variable. Now, when we now talk about first principle, we now break down that change, that process of change, into smaller bits. This time around, first principle is formed by considering the slight or smallest possible change that can exist within x and y. Dy dx already has considered the total change, right? Sometimes we also call it the total derivative. Later on, we'll see exactly what that means when we start considering total derivatives, partial derivatives. This is said to be the total derivative, which means you have considered all the possible changes that y can go through with respect to x. However, when we talk about first principle, we are considering the smallest possible change, those individual changes that you add up together to get the total change. So that is exactly how first principle is formed. So how exactly do we represent it? We represent it by utilizing the original equation. So we will take these equations and use them to explain first principle. Now we have y equal to x squared here. On this side, we would also have another one, y is equal to x. So we would have these two, and then we'll try to solve it. So we'll start with the smaller one because x is obviously smaller than x squared. We'll start with that, and then we'll come back to x squared, and then we'll bring it together. So, of course, from here, dy dx is going to be equal to 1. Same process. This is going to be 1 times 1, 1 minus 1. So that's going to be 1. Now, by first principle, let's see what exactly is going to happen. By first principle, first step says add increments both sides, right? Add increments to both sides. So let's put that into perspective. On the left-hand side, we have y. So we'll add the increment of y to the left-hand side. How do we represent the increment? We represent it by delta y. So this delta means the slight increase in y. that slight value that increases y. So y is the original, and this is the slight increase on it. On the right hand side, we will do the same thing, but this time we would increase by x. Very, very, very important. The next thing is we make, now this part is very, very interesting. The next thing is I can say we make delta y sort of the formula, but instead of doing that, let's take it step by step, step by step. Instead of doing this, let's say subtract y from both sides. So if we subtract y from both sides, here we would have y plus delta y minus y is equal to x plus delta y, x plus delta x minus y. Y cancels, so we have delta y is equal to x plus delta x minus y, right? Now we have subtracted y from both sides. Next thing, do not forget, substitute the value of y. And you're wondering, what is the value of y? Y has a value. Y has the value from the original equation. Y is equal to x. So that's the function that is assigned to y. So that means we have that delta y is equal to x plus delta x minus x. If this is the case, we see immediately that x will cancel. And then the fourth step says divide both sides by delta x. So we divide both sides by delta x. What do we have? We have delta y divided by delta x is equal to delta x over delta x, which immediately will give you 1. So this means that delta y over delta x is equal to 1. And then, icing on the cake, we evaluate the limits. Take limits as delta x tends to 0 to form dy dx. So now let's explain this. We have had delta y divided by delta x. At that point, we have said increase the small increase in y with respect to x. That is what we are having here. However, the moment we take the limit as delta x tends to 0, we are now saying that take the limit as that slight increase ceases to exist, right? If it tends to 0, it means you are saying that that slight increase does not exist. So if that slight increase does not exist any longer, it means that you have totally ignored the slight increase for the total possible increase. I take it again. If I have delta y divided by delta x, which is slight increase in y with respect to x, the moment I take delta x tending to 0, it means that I have said I do not want to consider the small increase any longer. Now I want to talk about the total increase. So taking the limit as the small increase tends to 0, which means as the small increase stops existing, then what I will have left is the total increase. So the limit changes the small increase into the total increase. By extension, I'm saying that dy dx will be equal to the limit as delta x tends to 0 of delta y over delta x. And if I evaluate the limit on the left-hand side, obviously it means that I will evaluate the limit on the right-hand side. But then what I have on the right-hand side is 1. So what this immediately tells me is that dy dx is equal to 1, which you see that is exactly what we have from our standard notation. So what do you see? You see that those standard notations you have, those formulas you have that we discussed in the last class, we were able to generate or discover those formulas through the rigorous process of first principle, just like we can discover the quadratic formula through the rigorous process of the completing the square method. Same thing. What this essentially means is that all of those formulas, if you had it in your head, that how exactly did we get those formulas? Do those formulas exist? Can we actually even use those formulas? You can use them because they have been proven to be true by first principle. So our focus in class today is to pick as many of those standards and to show them by first principle. Now I used this simple one so that I could write out the steps. Basically, whenever you do first principle, these are the 5 steps you are going to be doing. You are going to first and foremost add the increments to both sides. Next, you are going to subtract the original function, which is y. Next, you are going to substitute the value of that y using the original function. Don't forget that y is equal to f of x. And then after you have done that, you're going to divide both sides by delta x. And then the moment you divide, the next thing you do is to take your limit. So these are the major 5 steps that you do for first principle. You might add some few things later on based on the function you are evaluating, and we would see exactly what that means in this class. So let's take y equal to x squared. This time around, I won't waste so much time writing the steps. We are just going to copy the steps there so that we have more space. So step 1, we are going to add increment to both sides. In this case, it's going to be y plus delta y. And then on this other side, now do not make this mistake of saying, since I have x squared here, it's going to be x squared plus delta x squared. This is totally wrong. The increment is on x and not on x squared. So since you have x squared, it means you have twice the value of x. You have x times x. So instead of x squared plus delta x, which makes no sense, to be x plus delta x all squared. Does that make sense? The value, the increment, is on the variable. So if it's x raised to power 2, then the increment will be x plus delta x raised to power 2. Very, very important. Think about it this way. Let's say that you attend a birthday party and the celebrant is giving out gifts, and it gives you 2 sticks of blue wrapped sweets. 2 sticks of blue wrapped sweets. Now, he has given that to you. Then the wife of the celebrant now comes out and says, "Oh, sorry for that. If you have received a blue wrapped sweet before, actually what we should be giving you is a red wrapped sweet." Because you already have 2 of it, it's not as if you are going to give out those 2 wraps and collect 1 wrap of red sweet back. No. You are going to take 1 blue wrap, collect a red, and then extend the second blue wrap to collect another red. So you are going to have 2 blue wraps exchanged for 2 red wraps sweets. It's simple logic, right? So what this means is that if you have x squared, which is x times x, then your increment will also be x plus delta x times x plus delta x. That is how it's going to be. It's not going to be anything different. So be very, very careful about that. Do not think it's going to be x squared plus delta x squared. This is a mistake that a lot of people make. Do not make it. So this is very, very important. Now, we have done the first step. The next thing is we are going to subtract y from both sides. We are going to do that. That is going to give us delta y is equal to x. Now, of course, you have x plus delta x all squared here. So it makes sense for you to expand this. If you expand this, it's going to give you x squared plus 2x delta x plus delta x all squared. See how I wrote it? Delta x all squared, and then you have minus y. Again, very, very important. X squared. Now, you might be wondering, how exactly did I expand? Of course, this is going to be x plus delta x multiplied by x plus delta x. Now, if you take this, x multiplies everything in this bracket, and then delta x multiplies everything in this bracket. Now, in this case, it's going to be delta x multiplied by delta x squared. It's not going to give you delta x squared. No, it is not going to give you this because it is not delta x multiplied by x. No, it is delta x multiplied by delta x. So you have 2 of the same thing multiplying themselves. So it's going to be delta x all squared. Be very, very careful how you place your squares. Do not just place them carelessly. Make sure they are in brackets, especially if you are writing a theoretical exam. This is a very, very big deal. A lot of students make common mistakes like this that end up changing how your questions are answered. So then from here, we substitute the value of y. So that will be delta y is equal to x squared plus 2x delta x plus delta x all squared minus, now don't forget that y is x squared, so it substitutes and then you have something that cancels immediately. So anytime, the moment you substitute for y, there will always be something that cancels. That's like the very first thing that happens. And then we go to the fourth step, which says we divide both sides by delta y by delta x. So delta y divided by delta x gives us, here we have 2x delta x divided by delta x plus delta x all squared divided by delta x, right? Now, this will cancel, and this one will cancel one of it. So you'll be left with delta y divided by delta x divided by 2x plus delta x. Now, again, you see the reason why it's very, very important to write like this. Because if you are writing it as delta x squared, if you divide it by delta x, they would not cancel. There's no way they will cancel. It would be very, imagine if you now thought, okay, this one, the result will now be x, because delta x squared means that you have x times x. So this will cancel and your result is x. That would have been so terrible, right? So you have to be very, very careful how you write. And then you are here, and the last step says I take the limit. So if I take the limit, I will have that dy dx is going to be the limit as delta x tends to 0 of delta y divided by delta x, which is equal to the limit as delta x tends to 0 of 2x plus delta x, right? So in this case, it means that I have that dy dx will be equal to limit as delta x set to 0. It doesn't affect 2x because it does not have any delta x attached, but it affects this one. So it's just like saying 2x plus 0. So it means that your dy dx is equal to 2x, just as we had. So this is exactly how the first principle is solved, right? Basically, this is how it's solved. You see the big pattern. See that every single thing we did is based on those five steps. Basically, you're doing nothing other than those 5 steps. It's very, very important to keep those steps in mind. Of course, sometimes you might sometimes you might want to join the second and third steps together, subtract y from both sides and substitute immediately. That's fine. You might want to take the division and take the limit immediately. That's fine. Try to shorten it as much as you can if it's an objective exam you're writing. But if it's a theoretical exam, make sure you flesh your workings out as much as possible. Let me chip this in. In theoretical exams, you are doing mathematics and further mathematics. These are questions you might likely find across both of them. Your teachers would have told you, but if they have not told you, this is something you should also pay quick attention to. In your mathematics exams, your steps matter. The marks you are given is assigned with respect to your steps. So the more steps you have, the more your chances of getting more marks. However, in a further mathematics exam, your approach is what matters. So there is lesser need for more steps in further maths. They just need the correctness of your approach. So if you're having 10 steps in mathematics, you could solve the same question with like 7 steps in further mathematics and you will be fine. The reason why it happens like this is because there are more questions for you to answer in your further mathematics exam compared to the mathematics exam in terms of the range of it. Of course, in mathematics, you have different sections, splits across it. But then in further mathematics, you also have some specialized questions that is believed will take a lot of your time